Today, we will look at the second part of equilibrium, which is Kp. So I hope you have the basics of Kc clear, because remember that a lot of things are common, like how we write the expression, how to calculate the unit, and of course, this calculation of finding the equilibrium also. So I'm going to scroll through. You should have looked at this explanation already. Let's look at now gaseous equilibrium. Of course, we are looking at an equilibrium, a reaction in equilibrium, but all in gaseous state. So there are two terms that you need to be very confident. Partial pressure, which is the pressure that a gas contributes in a mixture of gases. So it's kind of the concentration of a gas, isn't it? Because it is the amount of gas in the whole, not the amount of gas, but the pressure in the total pressure. Second term, the mole fraction, moles of one substance relative to the total moles. So it's calculated as a fraction. So let's look at the partial pressure first. The partial pressure is remember, is the mole fraction times the total pressure. I'm going to highlight something here. So, but the mole fraction, remember, is the moles of a specific substance divided by the total moles. And therefore, the mole fraction, the partial pressure is the mole fraction times the total mole. Now, very important, we're talking about the moles at equilibrium. So very often in exam questions, you have the moles at the beginning of a reaction, and you're asked to find the moles at equilibrium using this Rice table. Okay, remember the Rice tables allows us to find the change in reactant and product, and therefore we find the equilibrium moles, which means that in this time we're kind of expanding this Rice table with the mole fraction and the partial pressure. So compared to Kc, we don't find the concentration, but we find mole fraction and partial pressure. Okay, so one very important thing, the total pressure is the sum of the pressure of each gas. Okay, remember the definition, and well, remember this means sum of. While the mole fraction, it's a fraction, so what is the total? It's 1. That's why you can always double check if you have a specific type of exercise, or well, sometimes you can really double check if you did it right, yeah, because the sum of the mole fraction it's 1, and the sum of the partial pressure is equal to the total pressure. Okay, so it's useful to know how you can double check your the values that you calculate. So the expression, we're looking at an homogeneous system. So this is when reactants and products are in the same state, but specifically it's a gaseous system. So this is the reaction, remember, reversible reaction, and it's just the concentration, that's not the concentration, but it's the products over the reactants. Okay. This time we use these brackets to just include, the partial pressure of that specific substance. And then again, it's to the power of the stoichiometric coefficient. And remember, any K, big K, it's the equilibrium constant. Now we've seen Ka, Kc, the equilibrium constant for concentration, Kp, the equilibrium constant for a pressure system, and then we will see also Ka, which is the acid dissociation constant. But remember, they're all calculated in the same way. This means that the units are also the same, yeah, just like Kc, we cancel them out, and the common pressure units, pascals, kilopascals, atmospheres. Unlike that, in this calculation, you have to do conversions. Unit conversions are more common for ideal gas equation calculations, as well as, what else? No, I think that's kind of it. Okay, but for this, you're going to be given a unit. However, as I always say, whichever calculation you're doing, it's super important that you check the unit. Okay, just as a habit, you should be observing your units all the time in case you have a conversion to do. So, do you remember the effect of the temperature on the equilibrium constant from GCSE, I think? However, here it's important too because it comes in exam questions. So let's explain this a little bit. For a system in equilibrium, you are often given the enthalpy. The enthalpy is important because it will tell you if the forward reaction is endothermic or exothermic. So of course, if the forward is exothermic, the backward is endothermic. And remember that an increase in temperature favors the endothermic reaction. Decrease favors the exothermic reaction. This is according to Le Chatelier principle, okay? From GCSE, but still important to know. Guaranteed marks if you're confident with it. So let's look in the case of Kp or Kc, anyway, this equilibrium constant. But remember that this changes the ratio of products and reactants. Okay, that's why it's the only factor that actually affects the value of K. So if we compare Kp and Kc, let's have a look at. Oh, I'm going to take some notes here. So increase in temperature favors the endothermic reaction. Now you need to link it to how does it affect the value of Kp or Kc. Trust me that this is an exam question, so worth to know how to answer it and even how to work it out, because I don't think you need to memorize any of this, but you need to be able to work it out. And I do like this, just make some sketches. So we have an increase in temperature, okay? I like to visualize the effect like this. We have an increase in temperature, okay? So this means that it favors the endothermic, because it wants to decrease it back, favors the endothermic. In this case, is the equilibrium shifted to the left, okay, towards the reactants. So what does that mean? This means that there is an increase in either concentration or pressure of A and to B, okay, which is in this case of this reaction. Or if you want to make it more schematic, of the reactants. So this means that the denominator of our K constant increases. So what's the effect on Kp and Kc? It decreases, okay, because we have now a bigger number at the denominator. So as you can see, I like to sketch it out like this. It's just I know for now, maybe it's easy for you or you feel like, oh, okay, I understand it. But imagine in a moment that you're in the exam with a bit more anxiety, you have to, work it out. And if you have a very schematic way to follow, a very logic way, it makes it a lot easier during the exam, okay? Because remember, the feelings are all different there than they're here. So let's do the same. Oh, maybe you can try. What happens if we have a decrease in temperature? Try to take some notes as I do it, like this nicely schematically. And so decrease in temperature. What does that mean? The equilibrium, where does it shift? Shifts to the right. What does that mean practically? That there is an increase in either the pressure or the concentration of anyway C and D, because it shifts to the right. Therefore, what does it increase? At the bottom part of our equation. Therefore, Kp or Kc will increase in value. Okay? Also notice how much easier it is to do it when you have the equation and the K expression written out. So I would always suggest you to, if you can have a visual aid, have it. So how can you calculate or discuss something about Kp and Kc when you don't have it written down, right? So always have that. Okay. Other factors and the effect they can have, if they have any. This is what they write in the exam questions, by the way, like, what's the effect, if any? That could be a tricky question. Anyway, a catalyst increases the rate of the forward and backward reaction. So the equilibrium is reached faster, but it doesn't change the Kp. Pressure and concentration doesn't change the value of the equilibrium constant. Why, if you have to explain it? So here you have to check how many marks the question is. If it's like more than two, you might have to explain because the relationship between the product and the reactant stays the same. It's an important point, easy to miss if we just take it for granted. Okay. So catalyst, pressure, concentration doesn't affect the values of Kp and Kc. Okay, for Excel students, if we have any here, you're the only example that needs to know the heterogeneous system. It's very, very simple though, because we're looking at Kc, its concentration, and we have systems in normally like even gases, actually, we can calculate the concentration if we have the right values. But anyway, maybe we have solutions or a gaseous system, which means that if you have a solid in there, you won't include it, because how can you measure the pressure of a solid? Which means that if we have a heterogeneous system, a heterogeneous means a different, in different state, it's not included. As simple as that. So I will skip this for now, and instead, actually, no, you know what? Let's go through it. Okay. So let's look at this question. We have the mixture of some substances, we have our gaseous equation, we have the total pressure, and we have that. So remember what we did for the rice table, because sometimes you have to do it also for the Kp calculation. So let's walk you through step by step here. We set up the rice table, and it's very important that you add in it what you know from the question. So here you need to read very, very carefully. Okay, what do you know from the question? You know the initial moles of PCl3 and Cl2, and then you know that equilibrium, what it's for. Okay, remember that if the reaction hasn't started yet and it's not stated in the reaction, the products, their value, it's there. After that, we can work out the change. Okay, find the change and therefore the equilibrium moles. Remember, the change is equal to, normally you find it from the product and their equilibrium amount, but that increases, while of course the reactants decrease in that same amount. After having found the equilibrium moles, remember that we expand this table with the mole fraction and the partial pressure. And I like to do it like this, a tidy included in this table. Mole fraction, remember, is the mole of each substance divided by the total moles. And if you try, you will get this value. Partial pressure, remember, is the total pressure times the mole fraction. We're given the pressure over here, so we would just time these values together to get this. Then we will just substitute the values into the Kp, and at the same time you can write down the units, because this will make the simplification of the units very simple. Okay, just like Kc, the unit cancel out, and then of course if it's like 1 divided by that unit, you would write it as a reversed power, because you don't want a fraction for a unit. And that is it. So I hope it's clear. I hope this work solution, relatively simple, but I just want you to notice how we combine what you've learned from Kc to the Kp. We're just expanding this table. Okay, so now we will go into a tutorial and we will do an exam practice, which means that I will suggest you to stop the video and try it out. And then when you're ready, we will do the work through together. And I would suggest you to give yourself time. If you're stuck with the question and you don't move forward, don't give it more than 2 minutes more of the number of marks. So if you can do this in maximum 3 minutes, great. If not, give a couple of minutes more, but otherwise just play and see the solution. Okay, so good luck with it and play when you're ready. So I've set up the rice table, and you need, sorry, just 1 second here, Okay, let's start actually from this exercise. If you tried the other one, good, but this is actually the first part that just makes more sense, for the lesson that we did and what we've explained. So once again, give it a go and play when you're ready. This first question is the one that requires the rice table. Okay, so we write down the equation, the products, careful with the balancing. If you copy things down, make sure you copy them right, and then you interpret the question. So we have the initial amount of 0.317 moles placed and heated until equilibrium is reached. At equilibrium, we have oxygen. So this is the value that we have, okay? Which means that at the beginning, we have the zero of the initial product. So what is the change? Well, it's going to be plus 0.12 moles of oxygen. So the other chains, remember, they follow the ratio, so it's going to be double that, minus 0.24, because remember that reactants decrease by that amount, product increase by that amount. So the equilibrium moles will be the difference between this, so 0.077, and then 0.24 here. Remember that we can now extend our rice table with the mole fraction, so the mole fraction would be the value of each mole divided by the sum. So the sum, if we sum this up, would be 0.437. So if we divide each by this number, we get 0.17, 0.549, and then 0.27. You can always double check if you did everything right, because the sum of all of this should be 1. Second part. Just one mark. So we really just need to apply the equation for the partial pressure. Remember, that is the mole fraction times the total pressure. So the mole fraction specifically of NO2 is equal to 0.17. And then the total pressure, we're given it here. Notice the units are the same, so no issue, times by 120. Okay, and we get, let's do it in the calculator together, because I don't have the value down, but I hope you did the correct calculation. So it would be 20.4. And then for correction, remember, we're writing just like if it was an exam, we write down the unit too, because remember that this unit, we can also put it in the KP equation. Okay, so I hope so far it's all clear. And let's go into the third part of this question. Of course, the first step is having the expression for the Kp of the reaction. As I said last time, you need it if you need to explain anything about the reaction, but also if you want to do the calculation, of course. Calculate the total pressure. Okay. In the Kp equation, we write the partial pressure. But what's the partial pressure? Is the mole fraction times the total pressure. Which means that if we consider this total pressure our little x, that's how we can write it down in the equation. So Kp, 59.7, will be equal to the mole fraction of NO, so 0.46, I'm going to write it like this, 46x to the power of 2, times by 0.23x. Okay, remember that this means 0.46 times by the total pressure, because we know that this is the partial pressure. Okay, so I hope it makes sense where we got that x and what that x means. Okay, and divided by, what do we have at the bottom? We have 0.31x to the power of 2. Now, of course, the first thing would be to expand this. And actually, I just want you to notice here for a moment, this is just an algebraic equation where we have one unknown, which is x. So it's algebra, isn't it? Okay. Let's solve it. Okay, we can do it step by step, or I mean, it's just now playing around with the power of x's. Okay, but the value that I got at the, actually, I'll go through it just in case, because I know not everyone loves math here. So 59.7 will be equal to, if we expand this, we will have a 0.46x squared times 0.23 divided by 0.31x squared. And the important thing is that the x squared cancels out because repeats, okay? No, sorry, like actually I would like to do it in another way. Because we can't simplify it, we can't really simplify it just yet, which means that it would be, like we can simplify this as, I'm going to write it down here, 59.7 will be equal to, if we do 0.46 times that by 0.23x, the number we get is this, which I would suggest you should just keep it in the calculator, but I will use as many units as I can to, for sake of rounding. And then it becomes to the power of 3 divided by 0.31x to the power of 2. Now we can simplify it. So this cancels out. And we are left with 59.7 is equal to 0.50631x. If we solve it, 59.7 divided by this number, we get x being 118 kilopascals. Okay, so as you can see, it's more the workout than actually, the explanation. Okay, so this is important. That's why I was highlighting so much at the beginning the meaning of the partial pressure and the equation. Okay, so I hope it makes sense, and I hope if you find a question like this in an exam, this was AQA 2023, you will be able to do it. Now, last two parts of the question, we have question part 4 and part 5. Yeah, once again, give it a go, and when you're ready, play it. Let's think about, so a smaller volume, what does it mean? It means that there is an increase in pressure. We know already, pressure is not temperature, not an effect on Kp, okay? Because we know that Kp is only affected by the temperature. But what about the yield? So an increase in pressure, the equilibrium has to counteract the change by shifting to the side with less particles, right? So increasing pressure, the equilibrium, I'm going to write it like this, the equilibrium would shift to the side with less particles, which is the reactant side. So the equilibrium shifted to the left. So the effect on the yield will be decrease. Okay? So yield decreases because if we have to explain it, in fact, here is just the state the effect or deduce the effect. So we don't have to explain it, but for sake of this explanation, we do it. Remember, the pressure is can only affect the yield, but smaller volume means increases pressure. Increasing pressure means shifted to the side with the lowest number of reactants. Or very important, if you have to explain it, you must say the lowest number of gaseous moles, or amount of gaseous particles, as long as you relate it to that. Okay, and of course, this is the reactant, shift to the left, therefore, away from oxygen means decrease. Okay, right, for the next one, lower temperature. Well, we know something from the enthalpy, that the forward reaction is endothermic. So, decrease in temperature. What does that mean? It means that the equilibrium will shift towards the endothermic reaction, so it's to the right. If it's shifted to the right, means that we have now more of the products. What's the effect on this equation? This value at the top, it's bigger. Yeah, so it means that, sorry, I read the question wrong. Look, I do the same mistakes. Anyway, just a bracket. This is about the Kp. The Kp value would increase. But the question is asking why the equilibrium yield of oxygen decreases. Okay? Because, and here, sorry, I have to record this again because I was talking about an exothermic and the equilibrium is the opposite. Left, reactants, and Kp decreases. Ooh, my apology. Okay, so I hope it makes sense, my mistake. Decrease in temperature, the equilibrium shift to the left because it favors the exothermic. You know why I got it wrong? Because I missed one of the sketches that I normally do. Exothermic equilibrium to the left. Okay, so if you have to explain it, why the equilibrium yield of oxygen decreases, it's just like that. Yeah, because a decrease in temperature favors the exothermic reaction, so the equilibrium shifted to the left. Therefore, there is a decrease in concentration of the product, and therefore the equilibrium yield decreases. That's it. Okay, so you see, if I need to double check sometimes too, when I go into the zombie mode, it's easy to make mistakes. So lessons for everyone on this. So I hope you got a nice exam practice with this. And as you can see, KP calculation are relatively straightforward, but sometimes there are some more difficult ones like this where we have to use the X and you need to apply a little bit of logic sometimes, like in this case. And of course, make sure you read the question carefully because sometimes, we get distracted like I did just now. And well, if you want to have a look at the rest of the practice questions of KC and KP, and the solutions are at the end. Make sure then you double check it, that to do all of the objectives. And if you have any questions, and if there is anything not clear and you don't fix it, revisiting these notes, let me know and I will help you personally. Thank you for joining and see you in the next lesson.